So I thought I'd just do a video trying to explain physics in a email is not easy. So yeah, so it's kind of an interesting problem. So you've got block A, which is moving, and then you've got block B which is initially stationary. Now it's talking about these ideal spring bumpers. So what will happen is that if you plotted velocity as a function of time for the two objects, object A would be moving along here until it collided, and then it would slow down. It doesn't immediately go to its final velocity, but it slows down like that. And then you have the velocity of object B, which is initially 0, and then it is going to it's going to speed up. Now the velocity of A actually could go the opposite direction. So here we're showing it's going the same direction as it initially went, but theoretically, depending upon the ratio of the masses, it could go the other way. And it looks like with this mass being smaller, I would expect that actually that this would actually go the other way. So A starts out as positive, and then it's going to go down probably like this, some negative value. And object B starts out at 0, and then when it gets hit, it's going to speed up like that, maybe something like that. And there is this point where they are going the same velocity. And that is the case where you have the maximum energy stored, because when they are going the same velocity, their relative velocities are the same. I mean, their relative velocity is 0 because they're both going the same direction at the same time. So this one is always going to go to the right. So this one will be going to the right, and it'll slow down, and it'll compress the springs, and at some point this B will start to move at a slower rate than this, and then they'll cross. Okay, so under this condition, what's happening is that what you would use, you probably did this, is that the conservation of momentum would be such that at this particular point the velocities are the same, like it is for an inelastic collision, but it's an elastic collision, and it's that one moment in time where they're both moving the same velocity. So at that point you can have one less unknown in your equation, and you can figure out the velocity of the blocks, both blocks, at that point in time, which is the final condition. So the initial condition is where they're apart. The final condition is when they're moving the same velocity. So that leaves you enough information to solve for this final velocity. And then once you have the initial final velocities, you can calculate the change in kinetic energy. And that change in kinetic energy has to be equal to the energy that's stored in the springs from conservation of energy. So let's go back to your question here. What was your question? So so the second part asks what the velocities are after the blocks are no longer touching each other. So what's happening there is you're continuing on. So there's kind of like an intermediate final value. This is part A, and then part B would be here, where they now, once they start moving relative to each other, so you've compressed them, they've reached the same velocity, then what happens is B continues to speed up further as this one, but this one's going to actually change direction at this point, and then it'll start going backwards, and then they'll separate. And the final one is where they have completely separated. So that is, I think that's answering that question. Right, so yes, the second part is you assume that they are different velocities, but you are conserving energy, you're conserving kinetic energy. Whereas in this part, the first part, the kinetic energy actually is lower, and that lower kinetic energy is stored in the spring. So we're not losing any energy. We're transforming kinetic energy into some of it into spring potential energy. But once the springs separate, then all of the energy has to be in kinetic energy again. And a lot of time, let's see, reading through the textbook, I found that where it derives some relations for such situations where two blocks collide with one at rest for elastic collisions. If it was these relations that got me the correct answer. What I'm wondering is what we would do differently for inelastic and elastic collisions. Yeah, the thing about inelastic collisions is if you plotted the velocity curves, is you would have A moving along, and you would have B stationary. This one would slow down, this one would speed up, and then they would both go at the same speed after that. So what's happening right here in this area is where we're losing the energy due to friction. So just before they hit, B is stationary, A is moving. They hit over a very short period of time. You're going to dissipate the energy, and then they're going to travel at the same speed, whereas when you have the two objects with the spring, they don't connect to each other. You do have this point where they are moving the same velocity, but then the spring energy is then transformed back into kinetic energy for both of the objects. And once the springs separate, then we're not dealing with any spring energy anymore. We're just dealing with kinetic energy. Okay. Yeah, so the only difference I'm aware of is the elastic collisions have conserved energy and the inelastic collisions lose energy. Yeah, so that is true. So hopefully that provides some insight.